Okay, so today we're diving into something I know you're really into as a philosopher, the philosophy of cosmology. It's basically where like the biggest questions we have about the physical universe, like bump right into these really deep philosophical questions about existence, about reality, all that stuff.
Yeah, it's a really interesting kind of crossover point. Cosmology, the science of how the universe began and how it's changing, it sort of bridges these two worlds,
Yeah.
science and philosophy.
Yeah, exactly.
And it's changed so much over the years. It used to be mostly theory, even
Yeah.
like part of philosophy, really. But now it's this data-driven science.
Totally. And to make sense of all this, we're going to be looking at the Stanford Encyclopedia Philosophy's entry on the philosophy of cosmology. It's like a roadmap to all the big philosophical debates about the cosmos. So our mission today is to pick out the juiciest, most philosophically interesting bits of modern cosmology, especially for, a philosophical mindset. We'll trace how cosmology has bounced back and forth between philosophy and physics, look at the unique challenges it faces, and really dig into those deep philosophical questions that just won't go away.
Okay, so right off the bat, one thing that really hits me is how the universe is totally unique. It's not like, I don't know, black holes or galaxies where we can see tons of them and compare.
That's it, yeah. That's a core issue, in philosophy of cosmology. There's just one universe, right? So for philosophers, it's like, what does it even mean to talk about laws of the universe when we only have one example? Is a law some, like, universal truth, or is it just a description of what we see in this one specific universe? It kind of makes you rethink the whole idea of scientific laws, doesn't it? If there's only one of something, how do you generalize? How do you go from this one universe to some, like, bigger principles?
That's the question. Our source calls it a historical science par excellence.
Yeah.
Meaning, like, we're dealing with a one-of-a-kind thing, the only one in physical existence. Any group of similar things, well, that only exists in, like, our theoretical models.
That's wild. And it's not just some abstract puzzle, right?
Oh,
I
yeah.
mean, the universe, the fact that it exists and what it is, that's the ultimate context for us as humans. Our whole existence is set against that backdrop.
You got it. That's the second big point our source makes. Cosmology isn't just about mapping distant galaxies. It's about the stage where human life plays out. So then you have to ask these deep questions about what cosmology can really tell us, about our place in all this, about what it means to exist at all.
It's pretty humbling, yeah. Now, the history of cosmology itself is really interesting. It wasn't always this, like, super quantitative, physics-heavy field it is now, right?
No, not at all. It has its roots in theoretical physics, for sure, like with Einstein's static model in 1917, and then Lemaitre's work. But it's crazy to think that in the 1960s, cosmology was still basically seen as a branch of philosophy.
Wow, that's a big shift, like, in terms of its identity as a field. What happened to move it over to mainstream physics and astronomy?
Well, a few things came together. First, applying atomic and nuclear physics to the early universe. That was huge. Suddenly, we had the tools to build detailed models of the Big Bang, when everything was super hot and dense. And then, of course, we got way better at observing the universe. Telescopes that could see all kinds of electromagnetic radiation, from radio waves to gamma rays, started giving us a ton of data.
So it went from being mostly theoretical to being shaped by actual evidence.
Exactly. All that data meant we could actually test cosmological models in ways that were impossible before. But this is where it gets interesting for us as philosophers. Has cosmology really left philosophy behind? Or are there still, like, core philosophical issues that are built in?
I have a feeling it's probably the second one.
Yeah, I think as we go deeper, you'll see what I mean.
Okay, so speaking of those, like, persistent philosophical issues, underdetermination seems particularly relevant to cosmology. It's a concept that always seems to pop up when you talk about the limits of scientific knowledge.
You're right, it does. Basically, underdetermination is the idea that, the evidence we have might not be enough to pick one scientific theory for sure. You could have multiple theories that all explain the same data just as well, even if they describe reality in totally different ways.
So from a philosophical perspective, it means we can never be absolutely certain that the scientific theory we've chosen is the right one, right?
Right. Philosophers often see this as a big problem for justifying scientific knowledge. They'd argue that for any theory, you can always imagine another explanation that fits the facts just as well.
But I feel like scientists look at underdetermination differently. Our source mentions a striking contrast between how philosophers and scientists usually think about it.
That's key. Scientists emphasize how hard it is to actually come up with those really good rival theories. It's not enough for a theory to just fit some specific data. Scientists want a theory that fits into a bigger picture, that's consistent with other well-established theories, and ideally can be applied more broadly.
So the bar for a rival theory is much higher in science than in, like, a philosophical thought experiment.
Exactly. Just matching a few observations isn't enough. A good scientific theory needs to tie together different phenomena and give us a coherent, unified explanation. And when we look at cosmology specifically, underdetermination shows up in some very unique and challenging ways.
Tell me more about those specific kinds of underdetermination in cosmology.
Well, our source talks about a few main types. First, there's the limited observational window. The universe is a certain age, right? And the speed of light is finite. So that puts a hard limit on how far we can see. We have a visual horizon, which is the farthest stuff we can see light from, and a particle horizon, which is the farthest anything could have traveled to reach us. There are parts of the universe that are like causally disconnected from us, meaning we can't get any information from them.
So there are parts of the cosmos that are, in principle, beyond what we can observe directly, at least using light.
Right. Our past light cone, the area of space-time where light has had time to reach us, that's the edge of what we can directly see. And that limits what we can definitively know about the whole universe.
That's a big epistemological problem, yeah. What's the next kind of underdetermination?
The second one is the physics horizon. A lot of cosmological theories involve taking our current physics and applying it to situations that are way beyond anything we can test in a lab. Like, think about dark energy or the inflaton field. The physics behind these things might only be observable through their effects on the cosmos, not in experiments on Earth.
So we're kind of using the universe as a giant physics experiment, but we can't verify those underlying principles independently.
Yeah, that's the issue. And that lack of independent verification is a big source of underdetermination. If we see something happening in the cosmos, is it because our current theories need to be extended in some new way? Or is it because our assumptions about the universe's makeup or evolution are wrong? Figuring that out can be really tough.
It makes sense. What other limitations contribute to underdetermination in cosmology?
Another big one is the global structure of space-time. It's really hard to figure out the overall shape and like the topology of the universe just from what we see locally. Our causal past, meaning everything that's had time to influence us, only tells us so much about the parts of space-time that are causally disconnected from us.
So the observable universe could be just a small, maybe even simple piece of a much larger and more complex cosmic structure.
Exactly. The source mentions small universe models, where the universe is actually finite and small enough that light could theoretically travel all the way around. If that were true, we could observe light that circumnavigated the universe and learned about its global properties that way. But unless that's the case, our local view doesn't tell us much about the universe's overall shape, including things like whether singularities exist.
That's a pretty mind-blowing thought. We could be living in a universe with a really complex shape and have no idea.
Totally. And then there's the issue of establishing FLRW geometry. The standard model of cosmology assumes that the universe is, on large enough scales, homogeneous, meaning it's the same everywhere, and isotropic, meaning it looks the same in all directions. This is the cosmological principle.
And that principle is the basis for the FLRW models, those models that describe the expanding universe.
Right. But just because we see the universe as isotropic from our one point of view doesn't mean it's actually homogeneous everywhere. We need another assumption called the Copernican principle. It basically says that our location in the universe isn't special or unique in any way.
So we're assuming we're not in some special spot where the universe just happens to look the same in every direction, even if it isn't homogeneous on larger scales.
Exactly. There's actually ongoing research trying to test the Copernican principle through observations, like by looking at the isotropy of the cosmic microwave background radiation as seen from distant galaxies. The Ehlers-Guerin-Sachs theorem is important here because it shows that if all observers see isotropic background radiation, then space-time must be described by an FLRW model. So that moves the assumption of FLRW geometry away from being a purely philosophical idea and towards something with actual observational support.
That seems like a big step in making our cosmological models more grounded in evidence. Okay, so the last kind of underdetermination is cosmic variance. This one seems really connected to the whole idea of the universe being unique, like we talked about at the beginning.
It is, definitely. When we compare our one universe to the statistical predictions of the standard model, we're basically treating it as just one random example out of a bunch of possible universes that could have formed from the initial conditions. The problem is that our actual observations sometimes deviate from the statistical averages predicted for all those possible universes.
Like those anomalies in the cosmic microwave background radiation, or the fact that we can't seem to agree on the exact value of the Hubble parameter.
Yeah, exactly. Those kinds of things. So
Yeah.
the question is, are these differences just random statistical fluctuations, stuff that you'd expect to see in any one universe? Or are they signs that something's wrong with our models, that they're incomplete or fundamentally flawed? Since we only have one universe to look at, it's hard to tell whether these deviations are normal or exceptional. It's a tricky philosophical question. How do you interpret statistical deviations in a system where there's only one example? It really challenges our usual ways of doing science.
It definitely messes with our ability to use statistics in the normal way. Let's switch gears now and talk about another big set of questions that cosmology has to deal with: the origins of the universe. It feels like, by its very nature, cosmology has to tackle this problem.
Yeah, it does, and it brings up a whole bunch of unique challenges.
Mhm.
In most areas of physics, the initial conditions of a system are important, but they don't necessarily need a deep explanation from within that particular field. They might just reflect the influence of the environment or be an arbitrary starting point for our analysis.
But with the universe, the initial conditions feel different, like way more fundamental. It feels like cosmology itself has to explain them.
Absolutely. And there's a lot of debate within cosmology about what a theory of the initial state should even try to do, what kind of explanation it should provide. It gets to the heart of what cosmology is really all about, what its goals and limits are.
The source points out that modern cosmology does have at least one clear target. The standard model says that the universe is expanding and cooling down from a super hot, super dense state, roughly 13.7 billion years ago.
Right. If you follow the FLRW models back in time, you get to a point where things like density and temperature blow up to infinity, and the scale factor goes to zero. It's not like there's a literal first moment in the sense of time existing before time itself, but the age of the universe represents the maximum amount of time that could have passed since that hot, dense phase.
And this whole idea of a universe with a finite past got a big boost from the singularity theorems, right?
Definitely. Those groundbreaking theorems from the 1960s, especially the ones by Hawking and Ellis, show that having a finite past with singularities is a common feature of a lot of cosmological models based on general relativity, not just the highly symmetric FLRW ones.
If I remember correctly, those theorems are based on some key assumptions about gravity and what the universe is made of.
That's right. They usually assume that there's enough stuff in the universe, enough matter and energy, to cause our past light cone to refocus something that's supported by observations like the cosmic microwave background radiation. They also rely on an energy condition, which is a restriction on the types of matter that can exist, ensuring that gravity acts attractively, pulling things together.
So under those conditions, which are fairly general within general relativity, it seems like the universe must have a past boundary in the form of a singularity.
Yeah, that's what the theorems imply. Now, the fact that they predict singularities is often seen as a problem for general relativity. One big concern is that singularities might be points where determinism breaks down, where the laws of physics as we know them just stop working, and we can't predict what happens.
But the source suggests that this might be more complicated than a simple failure of determinism.
It is. Singularities might mean that general relativity has limits, but it doesn't automatically mean we lose all predictability. For example, globally, hyperbolic spacetimes, those are spacetimes with a nice, well-behaved causal structure, meaning you can basically predict the future if you know the present everywhere can still have initial singularities, like in the FLRW models. So in those cases, the laws of physics might not apply at the singularity itself, but the evolution of the universe after that point can still be deterministic. However, some types of singularities do pose a more serious threat to predictability.
The other big criticism of singularities is that they seem to suggest that general relativity is incomplete, that it can't describe what happens at those extreme densities and curvatures.
Right, that's a valid point. We probably need a more fundamental theory, maybe a theories of quantum gravity, to describe what happens really close to or at a singularity. Without that, general relativity just hits its limits. So yeah, we probably need a deeper theory to fully describe the very beginning of the universe. Any attempt to say what happened before the Big Bang would almost certainly need such a theory.
And the singularity theorems themselves don't actually tell us much about what the initial singularity was like, do they?
No, they mainly just tell us that it exists. The exact structure of spacetime near a generic singularity is still an open question. The VKL conjecture, for instance, suggests that the early universe was a lot more chaotic and less uniform than what the FLRW models assume, with complex, oscillating behavior in inhomogeneous universes.
There might even be different types of singularities beyond the simple ones we usually consider.
And of course, the singularity theorems are based on classical general relativity, so they don't include any effects from quantum mechanics.
That's right. As you get closer and closer to singularity, those quantum effects are expected to become more and more important. Plus, the energy conditions assumed in the singularity theorems might not hold for quantum fields, which can sometimes have negative energy densities. This opens up the possibility that the universe might have gone through a bounce at a minimum size, avoiding a true singularity. Loop quantum cosmology explores this idea, suggesting that classical spacetime comes out of a more fundamental quantum realm. So the singularity might not actually be the absolute beginning, but rather a transition from a completely different kind of reality governed by quantum gravity.
Yeah, that's one really intriguing possibility. Now, no matter what the initial state was really like, the Standard Model's picture of the very early universe has some weird features that need explaining.
You mean things like how incredibly uniform the cosmic microwave background radiation is, even across vast distances that seem like they should have been causally disconnected in the early universe?
The horizon problem, right?
Exactly. How could those different parts of the early universe, which never had a chance to interact, end up at such a uniform temperature? And then there's the flatness problem, where the universe seems to have needed an insane amount of fine-tuning to be so close to spatial flatness at the beginning. Any tiny deviation from perfect flatness would have been magnified by the expansion.
It's like balancing a pencil perfectly on its tip for billions of years, right?
Yeah.
Super improbable. That's a good analogy. And then there are the initial density perturbations, those tiny ripples in the otherwise smooth early universe that eventually grew into the galaxies and clusters we see today. Those perturbations have a specific amplitude and a really striking coherence over large scales, which are also hard to explain with just the standard FLRW models.
So the early universe seems to have started in a very special, very specific state with these odd properties. How do cosmologists try to account for that?
Our source mentions a few main approaches to developing theories of the initial state. One popular idea is attractor dynamics, like cosmological inflation. The basic idea is that a period of super fast, accelerated expansion in the very early universe would have basically erased any traces of previous, maybe messy, initial conditions. It would have driven the universe towards being flat, homogeneous, and having the specific kind of density perturbations we see.
Inflation became the go-to explanation for these puzzles of the early universe, didn't it?
It did. It was a really compelling and unified way to explain the horizon problem, the flatness problem, and the origin of the density fluctuations. But even inflation has its own problems, especially when it comes to its own initial conditions. How did the inflet field, the thing that supposedly drove inflation, get into the right state to start that superfast expansion?
So we're just pushing the question of initial conditions back a step, it seems.
Yeah, that's one way to look at it. So that leads to the second approach. Maybe the initial state of the universe was just special from the get-go, no need for any earlier dynamics to explain its properties. Roger Penrose, for example, has long argued that the universe had to start with super low entropy to explain why we have an arrow of time. His wild curvature hypothesis says there's a specific constraint on the initial singularity requiring the wild curvature tensor to be zero.
So instead of a process like inflation wiping out earlier complexity, this view says the initial state was fundamentally simple and constrained in a certain way.
Right. And then the third approach tries to sidestep the whole idea of a single initial state for our universe by introducing the multiverse. The idea here is that our observable universe is just one small bubble or branch within a much bigger, maybe even eternal ensemble of universes. Each universe in this multiverse could have different physical laws or initial conditions.
Which, as you said before, just raises the question of where the multiverse came from and what its initial state was.
Exactly. So even dynamic explanations like inflation often end up relying on one of those other two ideas, a special initial state or a multiverse, to explain their own ultimate beginnings. Now, this whole discussion about the origin of the universe brings up some deep questions about what science can really tell us in cosmology.
It feels like we're hitting the limits of what we can know or even meaningfully ask within science.
That's the feeling, yeah. When it comes to the universe's origin, cosmology is missing some key features of other sciences. We only have one universe to study, so we can't do the usual scientific thing of testing laws and theories against multiple independent examples. Plus, there's no bigger system or context that we can appeal to explain the universe itself. It's literally everything.
So that challenges our usual ideas about what a good scientific explanation is?
For sure. Can we even talk about laws of the universe in the same way we talk about scientific laws in other fields? when we're dealing with a unique object and a unique event like its beginning. There are a lot of different philosophical views on the nature of laws of nature, and they have different implications for cosmology. Some might be okay with cosmological laws, like Penrose's whale curvature hypothesis, while others that emphasize repeatability or governing temporal evolution might not be.
And then there's the whole conceptual mess of trying to explain how the universe came from nothing.
Yeah, a lot of popular science tries to explain this, often by talking about quantum fluctuations in a vacuum state. But as our source points out, a quantum vacuum isn't really nothing. It exists within a pre-existing spacetime and has its own properties and fields. We have to be careful not to confuse those scientific explanations with the bigger metaphysical question of why anything exists at all.
These are huge questions that blur the line between physics and philosophy. Okay, let's move on to another area where those two fields overlap and often lead to debate. Anthropic reasoning and the multiverse. This seems like a very modern and hot topic in cosmology.
It definitely is. Anthropic reasoning starts with a pretty simple idea. The fact that we exist as observers means we can only observe certain kinds of universes, ones that allow for our existence. That puts a limit on what we can see and what kind of universe we can find ourselves in.
Dick's critique of Dirac's large number hypothesis is a good example of this kind of reasoning, right?
Exactly. Dirac noticed a bunch of large numbers related to fundamental constants in the age of the universe, and he thought they might be connected and changed together over time. Dick argued that our existence as carbon-based life around long-lived stars is only possible during a specific window of cosmic history, and it just so happens that Dirac's coincidence is true during that window. So it might just be a selection effect because of our existence, not evidence that the gravitational constant changes.
So anthropic reasoning can help us avoid being fooled by coincidences that are just a result of us being here to see them.
Right. It's about recognizing that our observations are inherently biased by the fact that we're here to make them. But using anthropic principles to explain seemingly fine-tuned features of the universe has been controversial.
Like using it to explain the universe's large-scale isotropy or why those fundamental constants seem to be exactly right for life.
Yeah. Some people argue that these unlikely seeming features are just necessary for any observers to exist at all. And lately, there's been a trend of trying to judge cosmological theories based on what a typical observer should see, using ideas from formal epistemology and how we deal with self-locating evidence, basically, how we think about our own place in a larger reality.
And that's where Weinberg's famous anthropic prediction for the cosmological constant comes in, right?
Right. Weinberg argued that there must be limits on how big the cosmological constant can be, because if it were much bigger than what we observe, galaxies wouldn't have formed, and therefore observers wouldn't exist. He went further and said that if there's a multiverse with different values of the cosmological constant in different regions, then we, as typical observers, should expect to find ourselves in a region where the value is within those limits, maybe even close to the average value allowed.
But that argument seems to rely on some big assumptions, like assuming that a multiverse actually exists and that we can apply a principle of indifference to all the hypothetical observers out there.
You're right. The idea is often that we should think of ourselves as a random sample from all possible observers. Nick Bostrom, the philosopher, has argued that we need this indifference principle to deal with the problem of freak observers, hypothetical observers, who might randomly pop into existence even in universes that are really unlikely to support life.
But this kind of reasoning runs into some serious philosophical problems, like how do you even define the group of observers that we're supposed to be randomly chosen from? That's the reference class problem. And how do we justify using a principle of indifference in this situation?
Exactly. Why should we assume we're typical or randomly selected in any way? And as the source points out, these principles can sometimes lead to weird, paradoxical conclusions, like the doomsday argument. So there's no real agreement on whether these new principles for anthropic reasoning are valid or useful. Another approach is to be more careful about how we handle selection effects within a standard Bayesian framework for evaluating theories.
So maybe we don't need those special anthropic principles to judge cosmological theories.
That's a significant view, yeah. Predictions based on what a typical observer should see might not actually matter that much when evaluating theories in a rigorous Bayesian way. Now, anthropic reasoning is closely tied to the whole puzzle of fine-tuning.
The idea that the universe, and especially the possibility of life, seems to be incredibly sensitive to the exact values of those fundamental constants.
Right. From the perspective of biology and how complexity arises, a lot of things about cosmology and fundamental physics seem incredibly fine-tuned. Even tiny changes to those constants, like the strength of gravity or the electromagnetic force, could have made a universe with no stars, galaxies, or complex chemistry needed for life. But from the perspective of fundamental physics itself, those constants are usually seen as contingent. We measure their values experimentally, but our current theories don't predict them.
So there's a tension there, right? Why do these seemingly random constants have the exact values they need for life to exist?
That's the core of the fine-tuning argument. It's intellectually unsettling. Shouldn't something as important as the possibility of life be explained by our fundamental laws, not just by the seemingly accidental values of a few constants? This unease gets worse if those life-permitting values seem to occupy a tiny, tiny sliver of the possible values.
But defining what counts as improbable or finely tuned in this context is tricky, isn't it? There's no obvious justified way to assign probabilities to different values for those constants.
Exactly. Trying to bring probabilities into this gets messy because we don't have a good theoretical reason to pick any particular probability measure. So there are a few main ways to respond to the fine-tuning puzzle. One is empiricist denial, which basically says, is this even a real problem that needs explaining? Another classic response is to say there was a cosmic designer who set those constants to be life-friendly. A third possibility is that future, more fundamental physics might show that those constants are actually connected or determined by deeper principles, getting rid of the apparent fine-tuning. And then, of course, there's the multiverse hypothesis.
Where the fine-tuning we see is explained by there being a ton of universes, each with different values for the constants.
Exactly. If every possible value for those constants exists somewhere in the multiverse, then statistically it's guaranteed that some universes will have the right values for life, and we as life forms will naturally find ourselves in one of those. Eternal inflation is one specific scenario that naturally creates a multiverse as part of the inflationary process.
But eternal inflation has its own problems, right? Like whether it's even testable and the measure problem, how do you even talk about probabilities in an infinite multiverse?
Yeah, those are big issues. Whether eternal inflation can make testable predictions beyond what regular inflation predicts is still up for debate. Some researchers are looking for signs of collisions between different bubble universes in the CMB, but those might not exist or be detectable. And the measure problem, which comes from having infinitely many universes in a lot of scenarios, makes it really hard to say what a typical observer should expect to see.
So the multiverse is a possible explanation for fine-tuning, but it has its own big philosophical and scientific challenges. And it relies on some form of anthropic reasoning, which we already talked about being pretty tricky.
Right, and throwing around infinities like that in multiverse discussions makes a lot of philosophers uncomfortable. The idea of actually having infinitely many universes and observers is a huge leap from what we know empirically, and it needs a lot of careful justification. Even David Hilbert, the mathematician, warned against using the concept of infinity too casually when talking about the observable universe.
So the multiverse is a cool and interesting idea, but it's still highly speculative and philosophically loaded. Okay, let's wrap up by talking about how we test and evaluate cosmological models in the first place. With the universe being unique, how do we even do science in this field?
It's a fundamental question. The basic hypothetico-deductive method, where a theory gains support if its predictions come true, runs into the problem of underdetermination. Different theories can often make the same predictions about our observable universe.
So just matching the data isn't enough to pick the right model.
Not by itself.
Hmm.
We need more sophisticated methods. A lot of philosophers and cosmologists argue that we need to consider things beyond just empirical fit, like how well a theory explains things, its internal consistency, how well it fits with other established physics, and its overall elegance and coherence. George Ellis has been a big proponent of this kind of approach to evaluating cosmological theories.
Sounds like we need a more holistic way to judge those theories, weighing different strengths and weaknesses.
Right. And the source makes an important distinction between what it calls cosmology, the scientific study of the universe, and cosmologia, which is more about what our cosmological understanding means for us, for our existence, values, and purpose.
It's a good reminder that even though cosmology is a science, its findings touch on some of the deepest existential questions we have.
Absolutely. If we want to engage with cosmologia seriously, we need to consider all kinds of data, not just observations from telescopes and particle detectors. We need to bring in insights from philosophy, art, literature, and all the richness of human experience when it comes to meaning and purpose. Saying that science definitively proves there's no purpose in the universe means ignoring a huge amount of potentially relevant information.
That's an important point. We need a broad, interdisciplinary perspective when tackling those ultimate questions. Well, this has been a really deep and fascinating dive into the philosophy of cosmology. We've explored the unique challenges of studying a one of a kind universe, the mysteries of underdetermination and the universe's origin, and the complex debates about anthropic reasoning and the multiverse.
And we've seen how cosmology, even though it's a mature science now with lots of data, is still full of philosophical questions and constantly pushing the boundaries of what we understand about reality and how far science can go.
So, to our listener, here's a final thought to chew on. Given that the universe is unique and all encompassing, what would even count as a truly satisfying explanation in cosmology? And how should philosophical ideas about explanation, evidence, and the nature of laws guide us when we're judging these grand stories that our cosmological theories try to tell? I highly recommend checking out the full entry on the philosophy of cosmology in the Stanford Encyclopedia of Philosophy and all the related topics it covers. Thanks for joining us for this deep dive.
Thanks for having me. It's been a pleasure.